So thank you and welcome everybody. So I'm Björn Fahller. I have been doing C++ for too long. I started full-time job first time in '94. So it's been going on for some time. Currently working for NetInsight in Stockholm. We do networking stuff. What I'm going to talk about today kind of relates a little bit about that. I should mention right away that this is a very superficial orientation presentation. It's you will not go away from it with deep information about a lot of details. You will have an overview. This goes for both coroutines and for IO U-ring. Also, I have a little bit of a cough. I don't think it's a computer virus, so you will probably not catch it from me, at least not from this session. But you have been warned. I may be occasionally noisy. All right, so networking in Linux. So what we traditionally use for doing networking is we have functions for receiving messages. So the second point, you do read or receive or rec message or rec multi-message to read data from the IP stack into data area. And a very simplistic program, you can, if you're just listening to one data stream, you can write a simple loop where you just read data into that and do whatever you need to do with it. And that works. And if you have a handful of streams, not very many, you can get away with spawning a few threads and do this. And that works. But if you want to serve a lot of data, hundreds of streams with thousands of messages per second, one thread per stream does not work at all. The operating system scheduler simply cannot possibly catch up. Plus, of course, you have all the scheduling issues. So what you typically do is you use the first point. You have functions like select or poll or epoll, where you register a number of file descriptors, that is network sockets that you're interested in what's happening, and you'll stand waiting until something happens, and then you loop over all the file descriptors where something did happen. And now you can partition the load a little bit so that maybe you can serve, you spin up as many threads as you have cores on the CPU, and each thread serves a number of maybe 50, 100 streams. That works. But there is a problem with this. So with the way you do this, typically you implement something like a poller, or you use a library that already supports this, like Boost ASIO, for example. But in essence, you still have the same thing, that you store the file descriptors that you're interested in receiving data from, in this case in the add member function. So register a file descriptor with some callback that does some kind of work, and then we have a wait function that calls the operating system to say, wake me up when there is data available, and then you loop over all the file descriptors that have data, read it, and do work with them. I should mention here in the wait function the magic number 1500 there for the size of the buffer. This is not completely arbitrary. I don't know if you're familiar with this, but in video streaming protocols, they are almost always implemented on top of UDP. And by default, the maximum payload size of a UDP packet is 1500 bytes. So in this kind of code, you often see this constant 1500, because that is the max size that you can expect to read from a UDP packet. So you read this, and then you call the register callback with the data that you read. This works, but what happens then is you call poll, and the kernel fills in some area with the IP stack, fills in some data buffer, and then you're released from poll, so you can read, and the read means that you're actually copying data from that in-kernel memory area up into your memory area. And then the kernel can start filling in something else while you are processing your data. And then you call poll again to wait for the next data. You will see that it's available. So let's see what actually happens when we do that. So I have a very simplistic program here. We have the poller that you just saw. There's a question about this 1500 bytes. Yeah, that is the MTU. That is exactly correct. So I have the poller as I showed you, and you can have a main program here. This is a silly example, but I'm reading from two sockets, localhost port 4000 and 4001, and I have something that just calculates the number of packets and the sum of all the bytes in the packets, and another function that just exits and prints these statistics on the exit. So we can create our poller, register our callbacks, and then we do poll and wait. So if we run this, by the way, for all these examples, I'm using G++11, and I'm compiling with C++20. So I'm using strace just to show what is happening here. strace is a Linux tool that shows system calls. So when I start it, we see a lot of things happening. But what's happening here is that we see the call to poll and everything is stopped. So what I can do now is, this is cool, by the way, if you're doing Linux networking stuff, Bash, the shell, implements as if they were devices in the device file system. It implements UDP starting points. So you can echo foo to dev UDP localhost 4000 actually creates a UDP packet from this string and sends it to port 4000 on localhost. We can do that. And now we see that we were released from poll, read out foo with the line feed, and then we're stuck on poll again. And we can call a few more, and it's the same. And then I can call to 4001 and print the sums and exit. So this is simple. It works. But there are a lot of system calls. Oops. So enter IOU ring. This is a fairly new system introduced in Linux. If I remember correctly, it came in the 5.1 kernel. And what it allows is for you to do operations with the IP stack or with the file system. Things that have file descriptors, but when preparing this presentation, I actually tried to use IOU ring with Stdin, and that did really not work well, just so you know. So IO-Uring is a lock-free shared memory data structure. That is, it's shared between your user space process and the kernel. And it has two queues. The submission queue, where you submit requests to the kernel to do things, and the completion queue, where you get information back that something has been done now. And IO-Uring is a little bit interesting in that it has two APIs. You can choose which you want to use. A low-level API, which is so low level that I'm not sure I want to call it an API. It's more like a description of how this lock-free shared memory data structure works and how you should manipulate it to make things happen. Or you can have the high-level API, which is actually not very high level at all, but it's fairly easy to use. So the high-level API is what I'm using in the examples here. So you include liburing. And what you do is you create a Uring instance. This is, of course, a C API. And you can have one ring per thread in a user space program. You give it a max number of pending entries for the ring. So 8 in this case would be pretty low for a normal streaming application, but never mind. And the way you do things then is to get the kernel to do something with the network, you get a submission queue entry, and then you prepare an operation. In this case, prepare read. Say, for this entry, read from this file descriptor fd and fill in the data into the data area pointed to by PTR and the size. And the 0 at the end is flag. We can ignore that for now. And then you can, I really should, use this Uring SQL set data, because this is the way that you can identify which operation was finished when you get information back from the completion queue. It's only one word, 64 bits, which means that if you want to associate both a callback and some data, you will need some kind of indirection. But 64 bits is plenty. You will be able to find a technique to store all the information you need. And by the way, these operations that I have showed here are all essentially completely for free. These are read and write accesses into just a fixed size array. This is dirt cheap. Nothing is happening here really. And then you wait. Wait for something to happen from the completion queue. You get an entry. And this wait can, of course, be, if there is no data available, it is a system call. So you maybe write something like this, a C++ ring thing. You really don't want this to be movable at all. The IO-Uring expects things to be in one place. You don't want to move them or copying them. Bad things will happen. But it looks pretty similar to the polar on this superficial level. But we need, here's one difference. With the polar, we just registered the file descriptor, and when it was released, we could read into a local array. But here we are actually saying to the kernel, read this data into this memory area. So we must provide it already beforehand. So in this case, I have this read work struct that contains a callback, the file descriptor, and the data area. In a real world streaming application, you would definitely use some message pool for received data. But let's keep the example simple. And then when we want to add work, we can make sure we create a destruct somewhere where we can reach it, store our work and our callback, get a submission queue entry and prepare the read, and store the address of the work so that we can find it when data arrives. Some nice guy added information to the slides that said what I just said. Interesting. So what happens here then is that when we run this, we have some data buffers that are already in place. And the kernel starts to fill something in, and we are waiting. But then we see that, the kernel starts filling in the next one immediately because there is one available, and wakes us up so that we can process this information. And then it goes on with, in this case, we have two buffers for the received messages, and we take turn. The kernel and our process take turn on which uses which. But we essentially have two threads here now. So the kernel can fill in data to one of the data areas while our process is working with the previous one that was filled in. So this is nice, and it actually gives us fewer system calls too, which can be important. So let's have a look at this. So the same program, but with the uring instead. So I have a ring struct here, the ring class, the one I showed you. Wait, this one is actually a little bit elaborate, but what happens here is that when we call wait, we call uring submit and say all these things that we have prepared, now is the time to actually do things with them. So here's a system call. And then we wait. If there is data already available, this will not be a system call. You will just get it. And then we do work with this entry. And with the work we do is, in this case, we call the callback. And I said that the callback can return a status saying that, yeah, and I want to continue, which is the true case, in which case we prepare the next read for the same entry. Or the callback can say, no, I'm done, I don't want to be here anymore. And then we just remove it from the list of pending work. And this completion queue entry seen function call is important. That is the way we tell this shared memory data structure that we are done with this piece now. So we do this, and then we have this peak that continues to just look at, and is there one more, and is there one more, and we work with that one too. And then the main program looks pretty similar to the one that we had with Paul. But in this case, I'm actually adding the 4 entries for reading data, so that we can have a queue of up to 4 pending reads, and we still have this 4001 that just prints and exits. So we do this one. We can see that we enter to the kernel to say that here is the stuff I want you to do, and then we have this wait, and there is nothing pending, so it will be a system call, and we're suspended, waiting for something to happen. And then it goes on. So this doesn't look like much of a gain, I guess, compared to the poll solution. But we can do another one. We can do strace-c. The C just counts the number of system calls, the number of each call, how many occurred. And here's another useful tool, nping. We're telling nping to create UDP packets to port 4000 at the rate of 1000. I don't know if this is actually a bug in nping or if it's working as designed. For numbers less than 1000, it's the number of messages per second. But when you enter 1000, it just goes full steam ahead, as fast as it possibly can. Send 20,000 packages, and with a payload length of 1400 bytes. And then when it's done with that, we end sending something to 4001 to stop the process. So we do that, and here we are. So it was a little bit too fast. We missed a few packets. This is because of the overhead with strace. It's definitely fast enough if you're not doing strace. But we see that for nearly 20,000 packets, we have a bit over 5,000 system calls. So roughly 4 packets per system call. Interesting. So let's compare that with the poll solution instead. Doing the same thing. Go, and yikes. 6,000 packets. We sent 20,000. We already received 6,770. And we see that we have roughly 2 system calls per packet, which is costly. This is not for free. So IOU ring is good in this respect. It can really boost your performance compared to the classic poll and read. So that was the first part of the talk. So now let's pause this for a while and go into coroutines instead. So change of topic, coroutines. So coroutines offers a way for you to write asynchronous code as if it were continuous loops. And we have language support for this from C++20. So it's there. C++20 compliant compiler supports the language bits of coroutines. And I am going to use the word magic quite a lot in the next few minutes. Sorry, but it really is. So you write code that looks like a loop, and the compiler converts it to something completely else via coroutine types that you must write. And they are mind-bogglingly hard to understand. It was so much pain to be able to write these types. And the standard library, unfortunately, does not offer very much of help. So this is a bit sad, I think. So what happens then, though, is we see an example here with 2 coroutines. Both are written as loops that just go around and do something. So the one to the right starts suspended. And the one on the left can now do some computation. It computes some x, and it suspends its execution and passes on the run privileges to the one on the right. It resumes and starts doing something with x. works with it, and when it's done with it, it suspends its execution so that the one on the left can resume its execution. Compute a new X, suspend its execution, let the one on the right continue with this and do some work, suspend its execution and resume, and so on. So, mind you, this is not threading. Everything that happens here happens in the same thread. So we have no issues with data races here. We don't have to worry about locks or whatever. And we also get good locality of reference with regards to cache, because copying information between CPU cores is really expensive with a cache, usually, not always. Sorry. So, what we do, we can write a coroutine, my coro. A coroutine that takes an X and a Y and a coro source, and we loop awaiting information from the source. And as long as we get information that is non-zero, we continue and do some work and add something to a result, and then we return it. And the bit at the bottom is quite important, that when we call the coroutine, what we get back is a coroutine object. And this one must be kept alive, because that one is what contains all the information. Because what actually happens is that the compiler sees the code on the left, and the compiler rewrites it sort of kind of like this. We get a class mycoro where we see that the local variables now became member variables, and the loop just isn't there. The loop is in the magic in impl at the bottom that gets values from the source and sees if they are non-zero, then it calls the function call operator, where we do the updating of our information. And then it goes on. And this is, of course, a vast simplification. The reality is not quite this simple. But as a first approximation to get an idea of what is happening, I think it works. It's not terribly wrong. It's good enough to get started. The crux here, though, is that this coroutine type is one that we must write. And this is also one that we must write. So if you look at the standard for C++20, it refers to these types as coroutine return objects, which is quite a mouthful and doesn't say a heck of a lot. Most blog posts and presentations from conferences I have seen refers to these as tasks. So good or bad, I will continue with this naming convention so as not to add to the confusion. A task must have a promise type, and no, it is not the promise. Don't go there. Don't try. It will not work. It will be very bad. So the promise is not a coroutine promise at all. And yes, we have to write the promise type. And the interesting thing here is that our task will be created from a promise. So the compiler generates code that makes sure that the task is constructed as a local variable, stack object, given a promise. And the promise is allocated by compiler magic. I said I would use the word magic a few times in this. And we must take care of its lifetime. And don't call delete on it. Ask me how I know. It will not work. It will be very, very bad. So what you do is you can create a smart pointer type. In this case, I use a unique pointer with a coroutine deleter. So the coroutine deleter, we get a coroutine handle from the promise, and then we can call .destroy on that one, and that will deallocate the object and do some other housekeeping stuff. Sweep some of the magic away so that things look normal again. And the promise, as I mentioned, is also a type that we must write ourselves. And there's a lot of ritual in this. This is pretty much as small and simple as it can get. Actually, it is oversimplified. It's simplified too much. Don't write one quite like this. Get return object, that is a function that is called by the compiler generated code to create the task. And then we have the functions initial suspend and final suspend. They must exist, and they must return one of suspend never and suspend always. Both of these types are empty types. They contain nothing other than the type itself is the information. But the compiler sees this code and generates its code accordingly. isReady and get are actually not used by the compiler. That is, these are convenience functions used to make it a little bit easier to write the rest of the code. So in our promise, we have a coroutine handle to a continuation. As you saw in this sequence diagram a little bit earlier, you have a coroutine that does something and pauses, hands over execution to the other one that will resume, and then it will pause and cause the other one to resume. And that is the way you can do this, by having a continuation that you say, now it's your turn, now it's your turn, now it's your turn. And I'm using an optional here to store a value, which is really kind of nasty, because this means that we cannot handle the error case with exceptions. But never mind that for the duration of this presentation. So yield value, what we do then is we store the information we got in the optional. So now it's possible to see that, yes, it does have information. And we call resume on the continuation so that it can do its work. And then to be able to co-await something, our task will need to implement operator co-await, which must return an awaitable. Also a lot of ritual again, and the awaitable communicates with the promise to know what to do. So await ready is when you call co-await on an awaitable, then it starts checking with the promise. Do we already have a value? If we already have a value, then we just get it. Otherwise, it suspends. So in await suspend, we get a coroutine handle and store it in the continuation. And now you may think, it's cool. Why do I have to store the continuation here? I can squirrel that away into some data structure and write a really awesome cooperative scheduler. And yes, you can. I'm really not sure that you should, but you can. I'm sure someone will do that and do something absolutely amazing. And I think others will do that and cause an amazing mess. But that's a different story. But that is how we get this running. And await resume is called when the coroutine resumes work again after a co-await, and then it just calls, in this case, the promise to get the value out of it. So we can actually have a look at this. So We have our types, and these are a little bit cluttered with trace things so that we can see what is happening. But otherwise, these are actually the types that I just showed. The task with the operator call wait and the awaitable. And I have a make that we will soon see why. And then I have a coroutine print all that just it takes a coroutine that is awaitable, and it just gets whatever the coroutine provides and print them. That is all. And we have some tracing in that one too. So in main, we get a coroutine handle called incoming that is done by just calling this make, and make just does suspend always. That is all it does. So what happens when you call make is you get a coroutine handle to something that is suspended. That's all. And then we call print all on this coroutine handle so it can get information. And now we have this coroutine handle. Note now that nothing has executed yet worth speaking of. We have just instantiated the coroutine types. So I can get the promise from this incoming coroutine, and I can call yield value, which will turn this machinery around. Boom, like that. So when we call it make on incoming task, we see that how the promise for incoming was created. Get return object is called, and then this creates the task of incoming, and it calls initial suspend. And from there, we're now here and call print all. Print all gets again the promise gets constructed. Get return object, we get the task for the printer, and initial suspend. And we see this print all. So it actually begins to do something, because the initial suspend here says suspend never. So it starts executing. But then it comes to co-await here. So it calls the awaitable, are you ready? And the promise says, no, I'm not ready, sorry. So we call await suspend, which means that we are back here now. So we can call yield value to the promise, which calls await resume to the suspended print, which will call get on the promise so that we can print the value. And so on, just over and over. And then when we come to the end brace, we see how these tasks and promise types are all destroyed. What we do not see is this trace saying print all is done, because we have not broken out of this loop. So as I mentioned earlier, the coroutine is an object, and every time we call wait it is called with a value. And since we have never paused it in any way, we are not running this. Instead, we're just running the destructor of the object. And this is safe. This is fine. This is not a problem. Excuse me again. But there's a lot of things happening. Definitely, a lot of things happening. But this is actually quite useful. We can do something. So here's an example of a super generic kind of thing to use with coroutines that are co-awaitable, because it takes some predicate and a task of whatever type, and we just co-await values and check the predicate, and if the predicate says, yes, this is a value that is in, we co-yield it. And then we go for another one. Co-yield calls the yield value member function of the promise that belongs to the task that is the return type. So the name yield value was not completely arbitrary. It's actually mandated by the language itself. Another thing we can see here is that there is not a one-to-one correlation between the number of things we co-await and the number of things we co-yield. We can co-yield several times for one piece of information retrieved, and we can co-await several values without co-yielding anything. And in fact, we can co-await from several different sources. That is perfectly fine. But we cannot co-yield too many because we co-yield to our task, and we are one. So let's do a really simple example. So have an is-odd predicate that just returns whether a number is an odd one. We can use this make that we saw earlier. And we can create this coroutine object odd values that is filtering in everything that matches is odd from incoming. And send that to print all. And then we just loop over them and yield the values, in this case, 0 through 9 inclusively. And we can see what happens when we do. So here's the entire program. I moved the task into a header of its own now just to save a little bit. But we have exactly the code that I showed you. Incoming is odd, get the odd values, the printer, and then we get going. So and we see that it printed the odd values. Okay, not rocket science, but this is a totally generic piece of coroutine function template that is useful in a lot of situations. So let's go back. We have chatted a little bit about coroutines now, and earlier we talked about IOU ring. So we have seen how IOU ring offers asynchronous data in a cheap way. And we have seen that you can call yield value on a coroutine promise, which starts to push data through a coroutine pipeline. And we have seen how to read values from an upstream coroutine with co-await, and how to forward values downstream with co-yield. So let's nerd out and put these together. I must warn you that the example program I'm going to show you now is extremely silly, because I don't want to burden you with how to do manipulations of video transport streams and whatever, because that's really a mess. So, not necessary, but a minor convenience, a way to get something callable from a promise type that just calls yield value on it. And we have our main function. We have some statistics, number of bytes and number of packets, and a flag tell you if we're done. So we have the line above what's marked now. We get the task of a span of char that reads from, that is going to be connected to read from port 4000. And this in 4000 we send to count packet data, which is a coroutine that just co-awaits these spans of chars and increments packets and how many bytes we have received, and then pass the packet on to the next one, whatever they do. We don't care. It's not our problem. And then maybe we want these in string format. They are now spans of chars. So we can have a toString that takes a task with spans of chars, co-weights these packets as spans of chars, and creates strings of them and co-yield them to whoever is the next consumer. And then we may want to strip trailing new lines. If you remember the first example where I just showed the echo foo to a port, you saw that it had a trailing new line. So we may want to strip such things. So we co-await strings now. And as long as they end with a new line, we just remove the end. And then we co-yield them. And the next one, we want to concatenate strings up to a length of, in this case, 40 characters. So we can have this concatenate2 that consumes strings and returns strings. But now we don't have this one-to-one correlation between what we read and, or rather, what we co-await and what we co-yield. So we have this string current line that is this is essentially the member variable that carries state across calls. So I have a loop where you say get the next piece, which we co-await. So the next piece is a string, and we check if the current length plus the length of the next piece plus 1 is too long. In this case, we pass on what we currently have, and we say that we store this piece we just received as the new current line. Otherwise, we just concatenate to the current line so that it can grow. So here is a coroutine that stores state between the awaits. So this is, again, it's an object where current line is a member variable that is updated in calls, and every co-await becomes a call. And then we have print lines, which doesn't really do anything surprising. I just added colons as delimiters here to make it a little bit more easy to see. And then we have our print and exit as usual. So we get a socket for 4000 and 4001. We connect the file descriptor to 4000 to this thing that just feeds the red data as spans of chars into this coroutine pipeline. And as earlier, 4001 is just the way to stop everything. It doesn't do any, well, and print the information. So let's have a look at this one. And I have forgotten what I called this program. It's the only one left. Coro. So count packet data, toString, strip trailing new line, concatenate to, print lines. And then we just add everything here to have all these coroutine objects that communicate with each other and does the work once we start giving them data, which happens here at the ring wait function. So if we run this, I'm just listing the devices I have on this machine and read the names and echo them to to this UDP port, and then end with the 4001 that stops the program. Boom, like that. And we can see how they just concatenated up to this maximum length. And at the end, we see that, 233 packets totaling 1483 bytes. This is powerful stuff. Just adding things like this. What you really have to think about, though, is that it's these coroutine objects that, well, not print and exit, print and lines. These coroutines objects, they are the ones that keep things going. If you let any of these be destroyed while the system is running, things will not go good. Things will not go well at all. So keep that in mind. So I'm pretty much done here, just wrapping up a little bit. So as I mentioned initially, this is a superficial walk around of just to show you the ideas of what exists here. And I've omitted a lot. So, for example, error handling is definitely not trivial. You need to think about how to propagate error information through these pipelines. A major omission is how to cancel things, and these are tricky in different ways with coroutines and IOU ring. The simple case with coroutines is the one that I actually showed, that I have some state for the entire pipeline which was the done flag. And when I reach that, I just destroy all the coroutine objects and everything is dandy, no problem. But if you have a situation where some coroutine somewhere in the middle says, I don't want data from you anymore, and wants to sort of push back, that is, you have to figure out a way to do that. Canceling from IOU ring has a completely different kind of problem, because as I mentioned when I introduced that, this is essentially multi-threading between your process and the kernel and its shared memory. So if you start deallocating the objects that the kernel may just this moment be writing to, things will not go well. So you have to figure out how you want to get those pending operations done before you can start deallocating stuff. And here's one really confusing thing. If you have looked at different blog posts or presentations like this one, but not this one, you have probably seen that the coroutine types look differently. And the reason for this is that the compiler, when it sees your coroutine types, it inspects them. There's a lot of freedom here. And the compiler sees, your types have these functions and this function and this function, and the signature for that function looks like that. Okay, I will generate code accordingly, which is mighty powerful. But it really doesn't make learning any easier. So I'm not jealous of the trainers that will write training material to teach us how to do this, because the design space is so large. So some conclusions here. The lack of library support is super much a headache. There's just no way around that. And testing and debugging is absolutely terrible, especially since you write your own types for a future and task and awaitable, and if you get them wrong, it can be extraordinarily difficult to understand what the problem is. So actually, what resorted to do when preparing this presentation was this. Here's a extraordinarily simplistic const expert string type that can be used as a non-type template parameter. So I have written my types with these names instead and added this tracing to see that, okay, it's get return object for that promise with that name, because I will probably have several promises of type int and something went bad and I don't know what, but this way I can at least see what it is. and likewise for the functions then, I give it a name. Print lines returns a task void with the name print lines, and it accepts a task of strings with some name, whatever, and I can trace these. This is back in the early 80s, seriously. This is not impressive, but I failed to understand what was happening with my program until I did this, which this is not good. Seriously, this is not good. It might be that I'm not very clever, but this is problematic. But writing asynchronous code as if it were local loops is extraordinarily convenient. It makes life so easy once you have ironed out the headaches of getting these types done right. And connecting pipelines is amazingly powerful. So this can be used for so many things, like a parser, for example. You start with something that just reads the files and connects it to a lexer that gives you the tokens, and then pass it on to the next step, which generates ASTs and whatever. I'm not a compiler writer, so I'm talking nonsense, but you get the idea. Or for that matter, with like video streaming, you get the messages, you get the transport stream objects, you get the program identifiers, so you can filter out whatever you want. And so this is super powerful. This is also good for testing, because these coroutine programs that co-weight something and co-yield something, they don't care what it was that produced the data or what it sends them to. You can just feed them data in your favorite unit testing framework. That is amazing. So some resources. If you want to get into I/O Uring, Shuveb Hussein's the Lord of the I/O Uring is a great resource to get to understand how this works. Coroutines, presentations, etc. There are a lot. The reason I'm highlighting Pavel Novikov's talk is that is the one that made me understand what I was doing. The other ones, it just didn't click for me, but with this one, it did. I crossed out Louis Baker's CPP Coro because it used to be the next great thing, and as far as I can see, it's abandonware. It is written for the Coroutines TS, but it's not a product. You can look at a really simple one from Michael Svetkin, eCoro. And if you want to go into some really impressive stuff, look at libunifx, which combines everything I talked about today and more, and it's really powerful. And with that, I say thank you for your attention. This is all I had to say, and here's how you can contact me if you want to do that. Thank you.
Thanks for this great talk. I really find it amazing what one can do with coroutines, and we still have a long way to go with it too. So we are gonna have a bit of a conversation about that in the lounge, I guess. And so if you have some questions, and because we're like basically at the end of the talk and the end of the time, join the table with Björn, and then all your questions can resume there. And see you there.
All right. See you in a bit.